The broadcast is now starting. All attendees are in listen-only mode.
Good morning, good afternoon, wherever you are in the country. It's Mark from SolidCAM. We'll be doing SolidCAM Live today, half-hour free training session. With me, as always, is Kevin Rankel. Hey, Kevin, how you doing?
Doing good. Hey, everyone.
Okay. So we didn't receive any questions before today's class. So one of the questions I get a lot that I want to cover today is why do we get you to do the coordinate system before the stock? And it's a pretty simple reason, in my opinion. We get this question a lot because of other softwares, they get you to do the stock first, and then you can do the coordinate system off that. So let's get into an explanation as to why we do that. And as per one of the requests of someone online with us, pitter patter, let's get at her. And if nobody knows what that is, I had asked in one of the question periods from last week for a proper intro, and that actually came from Jake. That's a line from, it's a Canadian TV show that it's current. I've never seen it. I hate that I've never seen it. I should probably turn in my maple syrup, but I never seen that show. So, but that is a line from the show. So here we go. Fan service to Jake. So thanks Jake for that. Okay, so coordinate system before stock. Why do we do that? Well, very simple. When you get into SolidCAM, when you do your tools, SolidCAM new, you're starting from this solid here, your target solid, whatever shape this solid takes. Now that is a representation of the target solid, the final part. You're not starting with the stock. So if this is the case, which is most common the case, then you don't have a stock to base your coordinate system off of. So you have to define your coordinate system somehow. And that's what all those options are for. Basically, top corner, bottom corner, it's going to approximate off of your target solid what the shape of the eventual stock will be. More often than not, it's either some sort of cylindrical billet, some sort of bar stock, or in the case of milling, it's some sort of box, length, width, and height. So that's why top corner, top center, bottom center, all those make sense in that respect. We don't have a solid model to work off of for your stock. We're working off the target model. That being said, with the idea in the future of some sort of, let me just get something on here, top center of model box, let's say. I choose this face here, and it gives us what we call the minimum extents box. This is not the stock. This is just the outside edge of the part. This is flush on all sides, or if it was a cylindrical part, this would be tangent with all sides. This is just the maximum version of the part. And again, this is not stock. But what we're doing here is we're using this to orient our coordinate system. You can actually see that it keeps the directions, even though X, Y, and Z are different directions, it keeps the same directions as the SolidWorks coordinate system, but it is separate. So Z is perpendicular to that top face. That gives us some sort of orientation to start with. But this is still in the same directions that eventually when you do your stock, let's say when you use the box definition, which is again a very common stock definition inside SolidCAM, this will give you the length, width, and height directions for that box definition. So again, you don't have a 3D model that represents stock, but at least with this, you can add the dimensions on outsides when you do the box definition. But knowing that we're going to do that in the future, let's say we know we have about 80 thou on the top face of this part. We're going to face off, or whatever we're going to do on the top of this part, there's 80 thou material, and we want that to eventually line up with our box definition. We haven't gotten there yet, but we know we're going to do something like that. We can do modify by delta. So as soon as we choose this top face, we know that Z is perpendicular to that face. Now we have an actual Z direction. Because remember, until you put this Mach 1 position 1, this coordinate system, you don't actually have any directions. And that is another thing that's very apparent when you have a part that's askew. If any of you have seen the part askew video, you know that sometimes these SolidWorks models come in at a weird angle. And that is another reason why you want to do your coordinate system first, because if that part inside SolidWorks has a weird angle, a weird direction, well, that stock solid could also have that weird direction. Anything could be possible with the parts you're bringing in. So once you get inside SolidCAM, you want to actually give it proper reference points. And this right here gives us that proper reference point. As soon as I set up proper angles of my X and Y, I have a direction for X and Y, or in this case, Z, and now I can put in my 80 thou. So even though this is set to top center model box, when I set that to 80 thou, it is 80 thou in that Z direction. So eventually when I get out of here and confirm all this, and then get into my box definition, I now have a direction for X, Y, and Z, or length, width, and height. And I know on the Z positive side, I'm going to put in 80 thou. Once I choose my solid there. There, so my 80 thou. So now my Z equals 0 face, when I set this up on the machine, being the top of my stock, is also the top of the stock here. So we get you to do it first, only because sometimes you don't have something that represents that stock. But knowing that you will put in this much material, or maybe even knowing that later on you will add a 3D model, you have the ability to do some shifts of your coordinate system for the eventual definition of your stock, whether it be a 3D model or this box definition here. Now, with that, got some questions. What is the advantage of choosing top center? From my experience, it's just a preference, I think. Kevin, what do you think? There's more.
The reason why I would definitely prefer top center than anything else is because majority of the machines out there come with the probe. So when you go to probe up your part, it's much easier to do a probe web and much accurate than it is to probe off of a corner. So this really works well with your like saw cuts. So it will always go off of the center of your part. So if you have a saw cut on your both X positive and X negative direction, it's going to center that as well as your Y direction. Now, Jake, you're saying, you know, wouldn't it be harder to indicate? Yes, it would be harder to if you're using an edge finder and indicate it that way. But like I said, I would say majority of the machines out there are taking advantage of the probe and probing up their part that way. And that's why you'll see a lot of us stay with that center, top center, versus going off to the upper right-hand corner or, you know, upper left-hand corner.
Makes sense. Because the shops I used to work in, they were much poorer, so they didn't have probes.
Yep.
And we used those old school kind of edge finder, the one that spins. And I always used to do the corner because obviously that's how you do it with those ones. But Kevin's right. A lot more modern machines, a lot more sophistication nowadays. Especially if you haven't seen, SolidCAM does have its own probe module as well. So that's probably why that's a little more preferred nowadays, if not more accurate.
And Jake, you work at one of the most high-tech companies out there. You got to tell them you need probe.
Yeah. So now we can see why it's kind of it's a good thing and a bad thing to be familiar with Kevin.
Yeah.
Okay, so let's get out of this box definition. So another more basic thing about this window is the iMachining database. So another common question we get is, what is iMachining? What is this iMachining database? Well, most of you on this in attendance today, I think you have iMachining. If you don't, iMachining is our proprietary optimization toolpath. It's there's 2D and there's 3D, and essentially what it is it takes information about your machine, your material, the dimensions of your end mill, and it calculates an optimized feed and speed. Now it does that off of, like I said, the machine, the material, and dimensions of the end mill. The end mill itself is pretty simple. You're giving it a dimension, you're giving it a diameter, a length of cut, number of flutes, the material it's made out of, all that kind of stuff. That makes sense. That's very common knowledge in our industry. But what is it about the machine and the material that you need to put inside SolidCAM for iMachining to work? And that's this lower section here. Once you actually have these part of your database, you'll never have to enter them again. You can just grab it from these pull-down menus, and then you're ready to go. One thing to note is that we actually come preloaded with a few machines. I have a few here, but the ones that come preloaded inside the software is the Haas SS, and I believe it's the Hermle. And then in terms of the material, you see a whole list here listed by their hardness. Now this is, again, a very common way to define your machines in a general sense, but in iMachining, at least from what I've heard, and maybe Kevin can correct me or back me up, but I've heard from our development, the guys behind developing iMachining, that it actually is probably a little more accurate to plug in specific information, the one we're about to do here, and that is the ultimate tensile strength of that material, because that is an actual value that's used in the science, the engineering of how we cut materials. Would you agree with that, Kevin? Do you think that's more accurate?
Yep, absolutely. So the general list in there is a kind of a dialed back general list. So if you don't know what that material is, you just know it's aluminum, you can grab one of the aluminums and you'll be safe. And by going off of the ultimate tensile PSI, this is the kind of almost just like the RA or the hardness value of that material. And so the software you guys can go, and Mark will show us, we can go right to a site and it will plug in the exact scientific results of the ultimate tensile PSI of that material.
Yeah, I was going to show off a little bit here and show you exactly what ultimate tensile strength actually refers to, just in case you weren't aware. So in material science, there's a thing called the stress strain curve. And I forget the symbols for it, but let's just say this is stress and this is strain. And usually for metals, the stress strain curve looks something like this. This area right here is elastic deformation. If you use the example of a paper clip, when you're bending that paper clip back and forth and you can return it back to its original shape without seeing any kind of bend or any kind of distortion, that's this area here, it's elastic. It just means that it just snaps right back to where it was. After this point, once you've added more forces, you're getting this sort of curve here. This is when you start to see the bend in the paper clip. And this is how cutting materials actually works. The ultimate tensile strength is about right here at the top, the ultimate strength that this thing can see. It's after this point that it's no longer really seeing too much stress, but it is seeing a lot of deformation. This is when the paper clip starts to actually get a little thinner, starting to what's called neck, because it's still deforming, but it's now just all the atoms and all the alignments in there are all broken. This thing's about to break, and then this is actually where it breaks, right here. So this is the value that you're going to get, like Kevin said, from a database or from your material supplier. This is where the chip begins to actually form. Basically, you've cleaved the material with that flute, and then eventually that thing is just starting to bend enough that it'll just snap right off. But this is where we need to know where the material is actually going to do that. So that's what ultimate tensile strength. That's just real quick there. But what that actually means for iMachining, what that means for SolidCAM, is it's just a number. It's a number specific to your material, but it's a number that you can look up and plug in. So let's look at the machine database and the material database, and that is right here. iMachining database brings this up here. Let's start with the machine because that's probably the easiest to describe. And when you do a new machine, let's just say we right-click, new machine, the highlighted information is all we need to provide. This right here, the maximum spindle speed, maximum feed rate in X and Y, and the maximum spindle horsepower. Let me just switch this to inch. And those are very easy numbers to know. Either you know your machine or you can get it from your operations manual. You can get that from your machine supplier. This is information that exists somewhere. And it's very simple. It's just from, let's say if we were defining a Haas, you go to the Haas website, you look up the data sheet for that machine, and you can easily find this information. Once you plug it in, iMachining uses that information to optimize the cut. It's going to try and take that end mill to machine that material on this machine and get as close to these feed rates, to these spindle speeds as possible. Now, in terms of material, there's actually one less piece of information you need to provide. Actually, before I move on, I forgot to mention that in the newer versions of SolidCAM, you actually don't even need to look this up. You can actually use what's called defined by VMID. And this actually, you can see the numbers are completely different here. This is actually reading right from the VMID file supplied to you by our post team. So rather than looking up your machine and having conflicting numbers, because if you've ever used iMachining before and you get that error that says something like spin too large or feed too large, it's because your iMachining definition is different than the definition from the VMID. VMID is the definition of your machine that you get from the post team. So if those two numbers are not the same, you'll get that error. So to eliminate that, and actually to make this a little easier, if the VMID numbers are correct, then you can just come here and just say defined by VMID. I have one called per VMID, and I have it set to 100, basically meaning that whatever numbers, feed, speed, horsepower, come from the VMID, it automatically gets loaded in my part file. So I actually don't even have to think about this anymore. I just have to make sure I choose the proper post with the correct VMID, and then my iMachining definition is already there for machine. In terms of material, we have something similar. You can see here it's kind of grayed out, but if the SolidWorks part is defined with the material, we can actually read the information we need for the material from the SolidWorks part. But let's say that's not the case. Let's say you actually have to define your material. In defining your material, it's the same thing. You'll just right-click anywhere here. You'll say New Material. And again, the highlighted information is all we need to provide. In this case, the ultimate tensile strength, like we were just talking about. Now, what that actually means, I kind of spent 2 seconds on it, but overall, you're not going to need to worry what that is. You really just need to know that you are machining a certain material, and you need to look up that certain material to get this number. So let's say we look that up. I'll just open up my web browser here, and we usually recommend people go to matweb.com. Matweb.com is a material library website, and it has all kinds of materials on there, all kinds of information about the material. So let's look up a really common material. Let's look up 6061. You can see it, I already have it on my list here. When you get to MatWeb or any kind of search like this, even just a general Google search, type in whatever information you know about your material, in this case, 6061. And then from the search results, choose one of those results that best matches what it is you're machining. So let's say we're doing T6. I'll just click on the results for aluminum 6061, T6. I'm looking for the ultimate tensile strength. And MatWeb gives it to you in metric and inch, but most likely I'm sure everyone's using inch. So 45,000 PSI. That's it. That's the number that I'll take, come back to SolidCAM, and then just type in 45,000 PSI under ultimate tensile strength. And again, that number gets used to find out how hard we can push this material, how fast and hard in terms of feed rate, but how much of a chip thickness, how much chip load we're working with when we do these tool paths, both in 2D and 3D. The rest of that is not currently highlighted because it's not entirely necessary. You can see there's a lot of auto calculation here, but because this is an optimizing toolpath, you want to put as much information as you can to really dial it in, to really get specific on your material and your machine. So in this case, if I knew that there is a maximum cutting angle for this material, if I do any more or any less, maybe I'm going to get a ribbon, I'm going to get dust, whatever material you're machining. That might be more for non-metals, but generally all this information here is to really fine-tune the machining of whatever material you're defining. Now, one in here that has always been kind of a confusion for me until basically yesterday. We had some internal training on this specific new window here. And the machinability factor is the idea that even though we've put all this information in here, and we're trying to optimize this as much as possible, there's still a lot more theory here than application. So you want to kind of have something where you can kind of fudge this a little bit to make it more realistic. So the machinability factor is just your way of taking these values and then plugging in just a little extra parameter to kind of make this more realistic, more dialed in for your specific machine and material. Let's say this 6061 is 45,000 PSI in general, but maybe this particular grade of 6061 has a little bit more, a little less of internal components, so it's probably harder than normal or softer than normal. So with the machinability factor, what you'll actually do is, let's get out of here. Let's get into an actual, I'm going to go to a part that actually has some iMachining already plugged into it. Let's go to our part from yesterday because that has some iMachining toolpaths in it. At least I think it does. Yes, it does. Okay, so you can see I'm using the per VMID, and then I've got my 6061 assigned. So if you go into a, let's say, 2D iMachining, first thing you'll note is as soon as I choose my tool, so let's just choose a tool, because of the definition of the machine and the material, when I get to my data tab, the feeds and speeds are locked out because that's calculating feeds and speeds for me based off the machine, the material, and now the dimensions of the end mill. When we get to the technology wizard section, this machining level is just how aggressive that toolpath is going to be. And the main focus of iMachining is that chip thickness. So all that information we plugged in is to just make sure that we maintain a constant chip thickness. It regulates the feed, the speed, the cutting angle, regulates a lot of the stuff about the toolpath to maintain that chip load. Under modified cutting conditions, there's additional information you can plug in. So again, the more information you plug in, the more accurate, the more optimized the toolpath will be. The one I want to address here is this required power at motor. This value right here is the theoretical amount of horsepower necessary to achieve this cut. So that's theoretical. On the application side, you'll actually see the chip load, the readout from your controller as to how much horsepower, how much actual raw power in reality was required to machine that same material with this toolpath. You compare those two numbers, and that gives you your machinability factor. You take this number divided by the actual number on the machine, and that will give you a number that you can plug in as your machinability factor. So for instance, let's say this one was 5.2 horsepower. I'm going to use these numbers because these were the numbers given to me in the training. 5.2 horsepower was required to do this particular toolpath, but on the machine, we read it as 6 horsepower. So we take a look at that. Let me just bring a little calculator over. 5.2 divided by 6, and now I'm going to go minus 1. That's about minus 14% of a machinability factor. It was actually harder. It took more horsepower to cut that thing than theoretically was expected. So that I would go back to my iMachining definition for that material in the machinability factor section and type in minus 14. Minus 14 machinability factor. Now I'm dialing it in even further for that material. Does that make sense for everybody?
Makes sense to me.
Because again, we're trying to optimize this. So not everything's going to be able to be captured by just a quick data entry like that. Some of this will have to be tested, basically. Yeah,
and like if we take aluminum, for instance, if you get aluminum from one manufacturer or vendor, and then you get another chunk from another aluminum manufacturer, that ultimate tensile PSI is going to be different just because of how maybe it was, you know, cold drawn out or what process they went through that. So that's why we have this machinability factor in there for you guys. So maybe when you guys are using a certain vendor, that machinability factor needs to be, you know, at 20%. And when you're using it for a different manufacturer for the same material and everything's the same, that manufacturer needs to be at, like what Mark was saying, at minus 14%.
Now, chances are you're probably okay with the number you plug in for your ultimate tensile strength. It's more for, like Kevin said, maybe it's a different supplier, maybe it's not 100% 60-61, maybe it is, but like you saw on the other screen, let me just bring that up. Sometimes that value does change per the temperature, or maybe it is in other materials, maybe it's annealed versus work hardened, or other scenarios where it is that same material, but some sort of circumstance has made it harder or softer. So a lot of that plays into this optimization. But generally with metals, steels, aluminums, you should be able to just plug in your ultimate tensile strength and you're okay. But the machinability factor does come into play a lot when you're doing non-metals. We had some customers that were dealing with plastics, and because iMachining was developed for metals, the machinability factor really came in handy to dial it in even further for that polymer, for that plastic that they were machining.
And when you guys are plugging in material, kind of like what Mark's saying, it doesn't have to be metal. We have a guy over in California using iMachining to cut his bamboo surfboards. We have a guy over in Washington that's using iMachining to cut 12-inch deep foam pockets. So just cutting foam. So don't think of iMachining as just going to be for your metals. REM board works fantastic on as well. So
yep. Or if you remember, I had that example of the woodworking guy doing those architectural railings. That railing being all curved had to be made out of a solid block of red oak. So one of my definitions that I helped them develop was red oak. And we had a machinability factor that was more on the positive side. It was actually easier to machine than certain materials like metal. Okay, so let's check out any questions.
Adding material or Matt Webb.
Yeah, mattwebb.com is a general website. It's not like a SolidCAM website. It's just something that is highly recommended by us. But if you do have your own source, definitely your material supplier should have a data sheet on that. I know a lot of suppliers up here that I used to deal with, they would give you that sheet with just all the different parameters, the hardness, the ultimate tensile strength. Even just the origin of it in some cases would be supplied. It depends on your supplier. Would MatWeb add materials if they're not already if they're not on there? I don't know. MatWeb is not our website, but I would say if you don't find your material on MatWeb, that doesn't mean that information doesn't exist. It just means that you'll have to find another source. If it's not on there, it might just not be a common material. I have dealt with customers that had a unique blend of a steel. I think it was like a proprietary one. I think it was an aerospace customer. In that case, definitely that information would come from your supplier, because if it's proprietary and it's unique, then they would have to do their own tensile testing to get that value.
Yeah, and one thing that I have noticed, if you can't find a material on matweb.com, sometimes there is a different name for it. So
that as well.
If you were, in your mind, we always call it a certain, we'll just go off 1018. We always call it 1018 cold rolled steel, but in maybe other places they call it a different style name or something like that. So you may just have to look up that as well.
Exactly. Yeah. No, you find that a lot with some very commonly used materials in certain industries. They've got their own name for it. So definitely that's, and in that case also, you can find it either on MatWeb using that unique name. Sometimes it's on there, or if you do a Google search, that's also an easy way to do that, because that unique name pops up in someone's literature somewhere.
Great questions, guys. Don't see anything else coming through though.
Perfect. Okay. Well, if there are any other questions, like always, I'll give you my email, and hopefully I can type it faster today. What you can do is send me an email with your questions, with your suggestions, and also if you are interested in getting personalized training, one-on-one with myself, with Kevin, with Greg, any of the guys on the team, always just contact your local sales guy, and they can give you a quote for some online training. If you already have training on the books, you can use my email to contact me directly, and I can figure out how to schedule on your schedule your personalized training. We use GoToMeeting, similar to the GoToWebinar we're in now. But in addition to that, you can actually call in, so you can actually speak with us live during the GoToMeeting. In addition to that, if you know anybody that could benefit from using SolidCAM, always remember that there is a finder's fee associated with that. So if you know anybody, just give us their contact info, or get them in contact with us. As long as we know it came from you, you get that finder's fee, whether they get into a demo or if they actually ultimately buy the software as well. We will continue this until, for now, I think it's just the end of the week, but I haven't heard any different. But I'm sure Kevin and I will find out if we're continuing, and if we are, you'll see an email with a new registry for the next set of SolidCAM Live. But we will continue this for the rest of the week at for sure 2 p.m. Eastern time every day until Friday, I guess. We will talk to you tomorrow. Stay safe. Hope your family stays safe. Everybody, we'll make it through this together.
All right. Have a great afternoon, guys.